Modern data infrastructure is no longer defined by how much information you can store. The actual constraint is the processing window, the time available to turn a raw data stream into a result the business can actually use. Every big data framework forces a specific trade-off. Choosing the wrong architecture can leave an organization with a massive bill for server memory it doesn't need, or insights that arrive too late because they were waiting on a physical disk. To identify the specific performance thresholds that separate these two frameworks, we analyzed enterprise deployment data with Royal Research. We map data needs on two axes: data volume and analytics velocity. Massive static archives sit in the bottom right, where volume is high but speed is low. E-commerce and fraud detection live at the top. In these high-velocity scenarios, delayed insights hold no commercial value. This evaluation uses your pipeline's coordinates on this quadrant to match your workload to its corresponding architectural framework. Hadoop is the foundational framework for big data, built to manage massive-scale storage across clusters of standard, inexpensive computers. Its distributed file system, or HDFS, takes a massive file, splits it into smaller blocks, and scatters them across the cluster. This ensures the data remains available even if a specific node fails. This makes HDFS a highly reliable and cost-effective method for storing petabytes of static data. To process that data, Hadoop uses MapReduce. This model works in a linear sequence. It maps the data and then reduces it into a summary. MapReduce relies on physical disk storage. At every step of the calculation, the system is forced to pause and write its progress to a hard drive before it can continue to the next phase. This reliance on physical hardware creates a significant bottleneck for any application requiring real-time answers or iterative algorithms that must pass over the same data multiple times. Hadoop functions like a heavy cargo ship. It is an efficient choice for moving immense, static historical archives, but it lacks the internal architecture required for real-time agility. Spark was engineered to solve that specific bottleneck. It uses a high-speed approach that removes the delays inherent in disk-based processing. Instead of writing data to a hard drive, Spark uses in-memory computing. It holds its datasets, known as RDDs, directly in the system's RAM during processing. To optimize this speed, Spark uses a directed acyclic graph, or DAG. It maps out the most efficient multi-path route for the data to flow, rather than following a rigid step-by-step line. Because it avoids the slow read-write cycles of a hard drive, Spark can achieve processing speeds up to 100 times faster than Hadoop for certain analytics tasks. However, high-performance RAM is significantly more expensive than physical disk space. This chart shows the dramatic difference in cost per terabyte between the two frameworks. As a company's data volume grows, the cost of the memory required to maintain Spark speed can quickly become the largest line item in an IT budget. Spark is a high-speed rail system. It provides rapid, immediate insights, but requires the enterprise to pay a premium for the memory infrastructure needed to run it. Beyond speed and cost, Royal Research finds we must look at how easily these tools handle different types of work out of the box. Spark has native support for real-time streaming and a built-in machine learning library called MLlib. Hadoop generally requires additional external components to perform these same tasks. There is also a talent requirement. Managing Spark typically requires engineers with specialized proficiency in Scala or Python, which can increase recruitment and retention costs. This matrix summarizes the core trade-offs. Starting with architecture, Hadoop relies on physical disks, while Spark processes in memory. Hadoop's primary strength is reliable batch processing at a lower cost, whereas Spark is built for real-time agility at the expense of high RAM usage. For workload flexibility, Hadoop is suited for historical archives, while Spark is designed for active streaming and machine learning. The final decision is a direct negotiation between your tolerance for latency and your budget for memory and specialized engineering talent. The choice follows basic transportation logic. You wouldn't use high-speed rail to move coal, and a cargo ship is useless for a daily commute. To select the right tool, we can follow a simple decision tree. Does your data pipeline depend on real-time streaming or complex machine learning? If the answer is yes, Spark is the appropriate framework. In sectors like finance or telecommunications, the speed of the result justifies the cost of the RAM. If you don't need real-time speed, the next question is, are you processing massive, static datasets on a strict budget? If the priority is cost-effective historical batching, Hadoop remains the standard solution. Many enterprises now use a hybrid approach. They keep the massive volumes of data on Hadoop's HDFS for cheap storage and use Spark to perform the high-speed processing on top of it. This hybrid configuration provides the final royal research verdict. Modern architectures often get the best return on investment by using Hadoop as the cost-effective storage bedrock and Spark as the high-speed engine that drives the actual insights.